Hey guys, what's up? Welcome to the next video on alcohols. This one is going to be covering ether synthesis. The next video is going to be covering how do we break apart ethers, and then we can go on from there. Alright, so let's get started. So first, what exactly is an ether? Right, so we're familiar with the normal alcohol, right? Like this, right? An R group, some sort of carbon chain to an OH. What an ether is if we take away the H and we draw another R, right? That's going to be an oxygen bound to two R groups. Now the R group could be the same or different, so I could put like this little prime symbol to show that it could be either the same or a different R group, all right? So let's see an example of an ether with regular carbons, right? So I can do something like this, all right? Or, that's a symmetrical one. How about something like this, right? So it's just an oxygen bound to two other carbons, okay? So how do we exactly make an ether, right? So a way that you guys have learned is called a Williamson ether synthesis, right? So it's Williamson ether synthesis, all right? And so what exactly does this look like? So let me draw some sort of alcohol, okay? Now what we do is the first step is going to involve a deprotonation of the hydrogen. Usually you'll see NaH, and this step 2 is going to be where we get the other carbon chain to our oxygen, okay? So I'm going to do H3Ci. And so let's take a look at the step by step. When we put NaH, remember these are separate steps. You have to write 1 and 2. If you wrote it like this, let's say on a synthesis question, they would take points off, okay? So the first step, we have Na and H. Na gets the plus, and we cross it out, and we have H minus. So if you remember, H minus, right, is a really good base, and we have an acidic hydrogen on our alcohol. So what it's going to do is it's going to attack this H, and this bond is going to break. So it's going to deprotonate it. O minus, and then here's like H2. Okay, that's step 1. Now in step 2, we're going to use our H3Ci, and now the O minus is a good nucleophile. So it's going to attack that carbon, kick that out. Remember, the iodine is a good leaving group. And we get this. Okay? So you can see that we essentially deprotonated the alcohol, right? And we then attach another carbon chain. Okay? And so definitely, let's go through the reasoning. We know about the Na and the H, right? The H is a strong base, so it can deprotonate the O minus. But what about this step right over here? Okay? So if you look, we had a good nucleophile, the O minus, right? RO minus, attacking this methyl with an iodine. Okay? Remember that methyls, when they have a good leaving group, undergo SN2 reactions, right? So this step, number 2, is an SN2. And so going off of what we know about SN2, what other reagents can we then use? So we've seen the methyl, CH3I. How about something like this? Right? This is just a primary alkyl chain, right, with our leaving group on a primary carbon. So this would also work for a Williamson ether synthesis, okay? So that is another way that we could do this. Rather than a methyl, we can attach we can use a primary alkyl halide. So how would this look? We again have O minus, then it would attack this carbon, kicking out the iodine, giving us this right here, right? Just count the carbons, 1, 2, 3, 4, 5, 6. We had 1, 2, 3, 4, 5, 6. Okay, so that's another way. We can use a primary alkyl halide. How about if I used as step 2? So let's use the same deprotonated alcohol. And step 2, I used something like that, secondary alkyl halide. Right? Now, if you remember, O minus, or RO minus actually, is a good nucleophile, but a good base. So when we have a secondary alkyl halide, we're actually competing with E2, right? So rather than forming an ether, we actually may form an E2. So like what could happen is this is going to take the hydrogen. This is going to go with this, and that comes up, and now we get this. All right, so it's really methyls and primary alkyl halides that you want to use. Okay, so now that was a Williamson ether synthesis. Now there is another way we could have done this through something called an alcohol dehydration mechanism. All right, and so typically for this sort of thing, we use an acid. So let's draw another alcohol. This is straight from one of your workshops. All right, it was a workshop quiz. Plus, okay, and so it gave this, and it asked what are the products, and it gave you three of them, three choices. So it was this one, this one, let me just move these, and then it was this one, and it was 1, 2, 3. All right, and they had the standard, so like the choices that you had was A, 1, B, 2, C, 3. Actually, sorry, I don't know why I did that. 1 plus 2. And then the last choice was all. So what's the mechanism here? Okay, remember alcohols are somewhat basic, and we have a proton, right? So bases like to take protons. So the first arrow, let's just start with this OH right here, the one on the left. Grab an H. Now this is going to look like this. All right. So now we have a protonated alcohol. So remember, this is similar to what we learned about alcohols in SN1 and SN2 reactions with strong acids. Now, if it's a primary carbon, it can't leave, right? So it can't just leave on its own and create a primary carbocation. So what can happen is we take a nucleophile, so our other molecule, and what it's going to do is it's going to take this oxygen and attack this carbon and kick this out. So what do we get? Here's our O, the H with it, and that methyl. This gets positive charge. And then we can have, like, let's say the water that just got kicked out, deprotonate this. Right? Giving us this structure. So that was choice 1. But, so let's look at what we did. We protonated an alcohol, right? And then the other alcohol that we had in our solution attacked. But what's to stop this compound right here from taking the H, right? They're both alcohols. This relatively similar pKs. So let's try it that way. So let's erase this. So now let's this grab the H. So what we get is and this is going to be a methyl with that water on it. Again, this is not going to be able to leave on its own and create a methyl carbocation. So what can happen now is our other group right here, other alcohol, can do an SN2 on that carbon to kick this out. Actually, so we're going to get and then the H2O can grab this again, giving us the same exact product as 1. Now, what about this? Let's erase this right here. So now let's say the molecule on the left again, that alcohol grabs the H, giving us this. We saw what happens when this molecule attacked. But remember, they never said we only have one of each in the solution, right? So what's to stop another one of these from reacting, right? So what we can have now is another one of those. So OH attack that carbon, kicking out that water, giving us this, right? So we're going to have this plus, and that water can now deprotonate this. And so that's going to give us number 2. So we have 2 of the products already. Now what happens if this was the one that grabbed it? The one on the left? grabbed it. Oh, wait, let's erase this. So now we had this, okay? And so we have, let's see, it's going to be protonated, right? And now how about if another one of these came in, right? Similar to what we just did before. So we're going to have now HO, CH3. The O is going to attack that carbon, kicking that oxygen and that water out, giving us this sort of thing. We have the hydrogen here, protonated, and all that happens is the water molecule that we kicked out before deprotonates that oxygen, giving us product 3. So you can see that the answer was actually all of them. And so that's something to watch out for. Unless they tell you we only have one equivalent or one of each, right? We can get all 3 of these products, okay? We can get an unsymmetrical ether like this, or we can get this reacting with itself twice, or just reacting with itself, and also the same thing here, okay? And so that's 2 ways that we can synthesize ethers that you guys have learned. There's actually a third that I showed in one of my videos, if you remember, for exam one, called an alkoxymercuration. What it did is it took a double bond, and it's very similar to oxymercuration, but we can have something like this then, right? And then we can have OR. All right. And so if you're wondering how that works again, you can check out the video that I have back in Oscar YouTube for oxymercuration and alkoxymercuration. It should be under the 3-membered ring pathway. And if you have it maybe written down, you could just use that. So I hope this video helped you guys. If you're still a little bit confused on something, please feel free to email me. Go to the CLC and ask the TAs. Or if you're watching this on YouTube, you can leave a comment and I can answer it so that others can see it as well. All right. Hope this helped you guys.